Hi all, today we are starting with the topic called modules. And modules, I understand them as doing linear algebra over rings. So the slogan is that modules are to rings as vector spaces are to fields. So let me try and explain what I mean. Fields are rings where all non-zero elements are invertible, and from linear algebra you know you have high proficiency with working with vector spaces over specific fields R and C. And vector spaces appear as natural structures in, so to say, real life. For example, you can picture C as a two-dimensional vector space over the field of real numbers. Also, if you took calculus 3 in UPenn or ordinary differential equations, I think that's how it should be called in general. Solutions to homogeneous ordinary or partial differential equations form a vector space over R. And you can take the ring of continuous functions, and you can see that continuous functions also form a vector space, an infinite dimensional vector space, also over R. We spent the last month generalizing fields to rings and setting up ring theory. And I want to say that modules are very similar objects to vector spaces, or at least they have a very similar definition. But as we will see later, just like rings, they have many peculiar properties that distinguish them from vector spaces. So modules is some sort of generalization of vector spaces for rings. This is what I mean by drawing this angle here. And they are also something that rings act upon. Let me recall the formal definition of a vector space. Let F be a field then a vector space V over F is a set with the following two operations. We have addition of vectors such that with respect to this operation, V is an abelian group. And the second operation, so let me write a triangle here not to confuse it with dot. The second operation is multiplication by a scalar, f times b goes to b. Multiplication by scalars. And these two pieces of data should satisfy the following axioms. Satisfying the following. So first, we want to request associativity. So for any pair of scalars x and y, and for any vector v in V, we want that x times y times v is x times y times v is the same as x times the product of y and v. We want to have right and let distributivity. So if we also take any, if we also denote the second vector from v by w, we want to have that x times v plus w is equal to x times v plus x times w. And similarly, x plus y times v. So want to distribute over sum of scalars times w. And finally, we want that the unity, the multiplicative identity of the field, acts as identity on vector. So multiplying by 1 does not change the vector. Okay, so that was the definition of a vector space. And now let me define a module by erasing words like field and vector space and replacing it with ring and module respectively. So now we take R to be some ring. R is a ring. And we say that a module I will denote it by M over R is a set M with two operations, addition, M times M goes to M, such that with respect to addition M is an abelian group, and multiplication by scalars, but this time we can multiply by elements of a ring. R cross M gets M to M. which satisfy the same relations. We have associativity for any two scalars from the ring and for any two elements of the module M. We have associativity of the action. We have distributivity. And if we assume that R is a ring with identity, if R is a unital ring, then we want the structure of a module to also reflect that 1 times B is equal to B. So I want to make a remark. That we can also consider modules over non-commutative or non-associative or non-unital rings. And these are also very important structures, but for now in this introductory course we will start with setting up the theory of modules over commutative, associative and unital rings. So from now on, again, R is commutative, associative and with unit. You can think that considering modules is some sort of adding more complexity onto the theory of fields, and you can ask why we want to study this. And so now I would like to give a hopefully motivating example of how considering modules can in fact enhance our understanding of various phenomena. So one example that was covered in Algebra 1 is the structures theorem of abelian groups. So if we have a finitely generated abelian group, then A is isomorphic to the free group on some number R of generators plus Z mod some prime number P1 to the power A1 times etc. Plus etc. plus Z mod P k A to the k. So in particular, if you take a finite group instead of a finitely generated group, you would see that A is isomorphic to a direct sum of finite groups, each of which is Z mod some prime power, and PIs can repeat. So we can view so if we have some positive number n, then n times some element A in A, we can write n times A as A plus itself n times. And if n is negative, we take we instead consider the additive inverse of minus m times a, where minus m times a is defined as here. And this defines a structure of a Z module on an abelian group A. Another example that is usually covered in Calculus 3 for ordinary differential equations or during linear algebra is Jordan normal form. So we take V, a C vector space, which is finite dimensional. We take a linear operator on V, and we can view this datum of a linear operator as a C adjoint X module. The structure of the module is defined as follows. So let's say that we have some polynomial f of x, and we want to define how f of x acts on this vector space. So we take some vector v, and I evaluate f at a, so I can consider powers of the matrix A, and I can add those powers with certain coefficients to get another matrix. So f of A is now a matrix which also acts on the vector space V, and I apply this matrix to the vector V, and thus I get a vector in V. Then Jordan normal form says that you can find a basis where your matrix A looks like lambda 1 through lambda k, and these are the Jordan blocks with lambda I equal to scalars lambda I, etc. lambda I, and off diagonal we have 1 through 1, 0 and 0. And I claim that this can in fact be transformed into a statement of about decomposing V into a direct sum as C X module. And without further explanations, because they would take another lecture or two, I would like to say that in fact these two phenomena can be unified, and this is called structure theorem. Of finitely generated modules over principal ideal domains. And this is pretty cool because on the first glance, abelian groups are very different from linear operators acting on vector spaces. But nevertheless, this more general viewpoint allows us to view these two examples of facets of one phenomenon. Now I would like to give some other examples of modules. So the zeroth example is 0. The zero module, which consists of one element, 0, and when we multiply by something, everything gets sent to 0. 0 is a module over absolutely any ring. Okay, so some less trivial examples. If R is a ring, then R with the structure of addition is an R module. And we define multiplication by recovering by using the multiplication on R. So this is called the free module of rank R. Oh, of rank 1. I'm sorry. So you can think that viewing R as a module over itself is similar to viewing some field F as a one-dimensional vector space over itself. And we can in fact define something like R to the power n as an abelian group. We can endow it with a structure of an R module. Where addition is element-wise and multiplication, multiplying vectors x1, multiplying the vector consisting of elements x1 through xn, but we multiply them all together. It's equal to r x1 dot r xn. So this is called a free R module of rank n. Next, if we take an ideal inside R, then I is an R module with the usual addition and multiplication by elements of R. And because of the absorption property, we know that multiplying I by any element of R would still put us in I. And using the usual associativity, distributivity, and unity axioms from the ring, we can verify that I is indeed a module over R. And one more example. If we have a ring homomorphism from R to S, then we can define an R module structure on S. And we define it as follows. So addition is inherited from the addition in S, and to multiply, to define multiplication, R cross S to S, we use our ring homomorphism phi. So R comma S. R times S would be defined as phi of R times S. So phi of R is an element of S, and we use multiplication in S to multiply these two elements. In particular, for any ideal I in R, the quotient ring is a module over R using the natural quotient map R goes to R mod I.